Hi everyone! Today we're going to be talking about the applications of exponential functions. Our objective for today is that students will be able to use logarithms to solve problems involving exponential growth, exponential decay, and compound interest, which are all real-world examples of everything we've learned in this chapter so far of logarithms and exponential functions. All right, so let's get started. All right, the first application that we're going to talk about is exponential growth, and this occurs when a quantity exponentially increases over time. We have a formula to represent exponential growth, and that formula is the function of t, so f of t equals a times 1 plus r to the t power. All right, where A is the initial amount, that's what you start with. R is the growth rate, and we always want it as a decimal. And T stands for time. All right, so here's an example of a real-world situation that involves exponential growth. So number one, we have the original value of an investment is $1,800. If the value has increased by 7% every year, write an exponential function to model the situation. Then we want to find the value of the investment after 15 years. So A is always our initial amount. So the original value of the investment is $1,800. That's our A. If the value has increased by 7% each year. So that's our growth rate. We're saying that it increased, that's our key word, it increased, it grew by 7%. And anytime if we see the word rate, we know it's going to be a percent, but we want to rewrite it as a decimal because we want to use decimals in our equation. So we would rewrite 7% as 0.07. We want to write an exponential function that models this situation. So we take our r and our a and plug it into our function. So we would say f of t, t being the number of years, equals our initial value, our initial amount, 1,800, times 1 plus our rate, 0.07, to the t power. T stands for number of years. And we can simplify what's in our parentheses, so we can say f of t equals 1,800 times 1.07 to the t power. That would be our exponential model, our exponential function, okay, that models this situation. Then we want to find the value of the investment after 15 years. So what does it equal? What does f of t equal? What does our function equal when t equals 15? So we're saying f of 15, when t is 15, we would say 1,800 times 1.07 to the 15th power. All right, then plug that into your calculator. Let your calculator do all the work. And we're going to get the investment after 15 years is going to equal $4,966.26. All right, so exponential models and exponential growth, one of the most applicable real-world situations is money. When you make investments, when you put money in the bank, it's going to exponentially grow, all right, because it changes based on the value you gain every year, and that's an exponential model. All right, so this is how exponential functions and logarithms apply to you and apply to the real world. I'm sure all of you love making money and watching your money grow. I know I sure do. All right, so this is how that happens. Remember, if you're having questions or you feel like you're getting stuck, raise your hand, call me over so I can help you. Otherwise, let's move on. All right, another application of exponential functions that we're going to talk about today is exponential decay. Exponential decay occurs when a quantity exponentially decreases over time. So the formula for exponential decay is very similar to exponential growth, all right? So the formula for exponential decay is f of t equals a times 1 minus r to the t power. So the only difference is we're going to say 1 minus the rate, that's decay, where in exponential growth it was 1 plus the rate. All right, and it's the same idea where A stands for the initial amount. All right, so what do you start with? R stands for, this time, the decay rate. So how much is it decreasing over time? And T stands for time. All right, so number 3 is an example of exponential decay. And unfortunately, I know we all don't like seeing our money go away or lose its value, but it happens. All right, this is a real world application of what happens when we make an investment that doesn't go so well. All right, so if we made an investment of $12,000, that's our initial amount. That's our starting, what we started with. And it's losing value, so it's decreasing at a rate of 4%. So 4% is our rate, and we always want to rewrite it as a decimal, so it's 0.04. We want to write an exponential function to model this situation. So let's first do that. We would say f of t equals our initial amount, 12,000, times 1 minus 0.04 to the t power, and then 1 minus 0.04 would give you f of t equals 12,000 times 0.96 to the t power. Now that's our function that models the situation. Now we want to find the value of the investment after 9 years. So when t equals 9 after 9 years, what is the value of our investment? Okay, so we would say f of 9, t is 9, equals 12,000 times 0.96 to the 9th power. Then we're going to let our calculator do all the work. We just plug in 12,000 times 0.96 to the 9th power. And we get that the value of our investment after 9 years, when it's losing value at a rate of 4% each year, is going to be $8,310.41. All right, and because it's money, you round to 2 decimal places. All right, just to the hundredths because we're dealing with money. All right, and that's our final answer. So I know none of us like to see our money disappear, but it happens. So we've got to know how to be able to calculate that. And this is an example of when we use exponential decay. All right, the last application of exponential functions that we're going to talk about today is compound interest. And this is probably the application that will affect you for the most part, probably have the biggest impact on you for the rest of your life. So when we're dealing with compound interest, sometimes you earn compound interest when you invest money into a bank, right? Then the bank pays you money and you earn that interest and it's compounded. Sometimes you have to pay out the interest rate. So if you take a loan, say for college or for a car, all right, then you have to pay the interest and it's compounded interest. All right, so we need to know how to calculate compound interest so we know how much money we should be receiving when we make an investment or put money in the bank, or how much money we're going to have to pay out when we take a loan. All right, and compound interest is calculated on both the principal amount, so the starting amount, and the accrued interest thus far. So that's why compound interest is so important, because it takes the money that you're gaining every year or the money that you're putting out every year, and the interest is applied to that as well. All right, so the formula for compound interest is A equals P times 1 plus R over N to the N times T power, where P equals the principal or the initial amount, principal, can't spell principal, or the initial amount, running out of space here. All right, R stands for the rate, N stands for the number of times it's compounded yearly, compounded every year, so we say yearly. And T stands for time. All right, so we're going to use this formula and we're going to do some examples that use compound interest. All right, so number 5 is an example of compound interest. So Laura deposited $12,000 into an account that earns 8% interest. So here she's going to be earning the interest. She puts money in the bank and the bank pays her 8% interest. So the initial or the principal amount is $12,000. That's our P. The rate is 8%. That's our R. And we always want to convert it to decimal, so 0.08. How much money will she have in 5 years? All right, so 5 years is our T. T is always in years. If the interest is compounded quarterly. So that's our N. And N is the number of times it's compounded per year. So if it's compounded quarterly, there's 4 quarters in a year. That means N equals 4. All right, so it's important to know how many times a year is that interest compounded. Then we're going to take all these values. We've got our P, our R, our T, and our N, and we're going to plug them into the formula. So A equals our principal amount, 12,000, times 1 plus our rate, which is 0.08, divided by N, the number of times it's compounded each year, to the power of N, which is 4, times T, which we know is 5. All right, then we're going to simplify this. We get A equals 12,000. And then if we plug this into our calculator, 1 plus in parentheses, 0.08 divided by 4, enter parentheses, you are going to get 1.02 to the 20th power. Then we plug this into our calculator, 12,000 times 1.02 to the 20th power. And we're going to get that she has $17,831.37. All right, this is how much money she'll have after 5 years if she earns 8% interest and it's compounded quarterly. That's a lot of money, all right? It's growing exponentially because it's taking the principal amount and the accrued interest. So you're getting the 8% on the money you've made so far as well. And this is really important because this is what you're hopefully going to make when you put money in the bank later on in your life, all right? This is a really good interest rate. You only hope that you can make this much money. It's not really reality, at least currently, right now in 2017. But this would be wonderful if it was true, all right? But this is how you would calculate that. All right, number 7. Here's another example of compound interest. So an investment account pays 3.9% interest compounded semi-annually. So let's break apart that sentence. We've got an investment, or an investment account. It pays 3.9 interest. So 3.9% interest is our rate, and we want to convert that to a decimal, so that would be 0.039. Now, this interest is compounded semi-annually. Semi-annually means twice a year. All right, so that means N equals 2. If $4,000 is invested in this account, so $4,000 is our principal amount, that's our starting initial amount, what will be the balance after 12 years? So when T equals 12. Now we're going to take all these values, our R, our N, our P, our T, and we're going to plug them into our formula for compound interest. So we've got A equals P, which is 4,000, our principal amount, times 1 plus R is 0.039 divided by N, which is 2, and then to the N times T power, so 2 times 12. Then we're going to simplify this. We get A equals 4,000. We plug this into our calculator, and we're going to get 1.0195 to the 24th power. Then we let our calculator do all the hard work. So this investment, after 12 years, we plug 4,000 times 1.0195 to the 24th power. And we get that this balance will be $6,358.48 after 12 years. And that's our final answer.